Calculus BC, we are looking at one of the most important lessons of the year. It's the chain rule. You can see our learning target up at the top. I can take derivatives using the chain rule. The chain rule deals with a composition of functions, a function that is inside of another. For example, when we look at y equals the sine of 2x, it's not just the sine of x, but the sine of 2x. There's a 2x inside of sine. So there's another function inside of the sine function, and that will influence the derivative. Now, we learned just the other day that the derivative of sine is cosine. So it's very tempting. I think so very often kids will want to say it's the cosine of 2x. Now, you've already learned the chain rule. I hope you know that that's not enough. That's not correct. I want to show you something. Look, we can go to our calculator, and we can say y equals, and under math, if I hit the up arrow to do this a little bit more quickly, we can go to a derivative. In other words, take the derivative, n deriv, and we're going to say there's our d dx of, well, let's take the derivative of the sine of 2x. Look at that. And down here it will say x equals. Well, in general, if you put in a 2 or a pi or whatever, it would say find the derivative at that value. Well, I'm just going to put for every x here, okay? So this is a nice way of saying take the derivative of the sine of 2x for every x that we're going to be graphing this in. Let's just hit zoom and maybe do a zoom trig. Come down here to number 7. And the wonderful thing that this is going to do, guys, is you are going to get this derivative graphed. Now, of course, you would say, well, I should get the cosine of 2x. And the cosine of 2x, you know, the 2 inside of that cosine of x function, that's going to affect the period. But look, your amplitude is not a 1. Your amplitude is actually a 2, isn't it? So, yeah, this is the cosine of 2x, but you have a 2 out in front of it. So, in case you were ever wondering, wow, is this really right? Look what would happen if we just graphed cosine of 2x. It wouldn't have the right amplitude, would it? It's not going up high enough. So that's a little bit of, what's happening here. You're going to have to take the derivative of that inside function. So you guys have seen this before, at least you should have in AMA. And this is the chain rule in action. You also get to see how you could graph a derivative using your graphing calculator. By the way, my mode was set on radians. Every time we take a derivative with trig functions, we're in the radian mode. The chain rule, if y equals f of x, well, y prime, and I hope you've heard this notation before, it's f prime of g of x times g prime of x. And super, super, super important. What you'll hear most teachers say is it's the derivative of the outside function. You can see there is a composition right here. You know, this is your inside, and, you know, right here you've got your outside, right? Your outside function is f, g is plugged inside of it. So take your derivative of the outside, you get f prime, you still have g of x inside of it, but then you multiply by the derivative of the inside. So without a doubt, this is what we're going to do time and time again. What I'm about to show you guys is really something that we won't do a lot of in our course, but, and I'm not going to put this on test, but you do need to see this for future reference. So many of you will take multivariable calculus, hopefully here at Maine East, but if not, you'll be taking multi-calc 3 at the university, wherever you attend. And you're going to find that when you take the chain rule for multivariable functions, you're going to need to know Leibniz's form of the chain rule. Leibniz's form of the chain rule is effectively this. dy dx, it's going to be dy du multiply times du dx. So very often when kids look at this, they will say, wait, don't the du's cancel out? It actually doesn't work like that. This isn't fractions that we're multiplying together, but it does lend support for why this is true when you just see this. Of course, you look at this, you'd say, what in the world is u? U is the inner composition. It's the inside function. Okay, so when we're looking here at example 1, it says y equals sine of x raised to the 5th. Another way you could write that, guys, is kind of like this. So in other words, you'd say, well, what's the inside function? Well, the inside function, we're going to say, let's let u equal the sine of x. Okay, that's really what's happening. And then you could say, well, I've got y equals u to the 5th. Okay, so at this point, you could say, well, how do I take my derivative? Well, dy du, if I took my dy du, you'd say, I'm just going to take my derivative as normal. I'd get 5u to the 4th. But wait a minute, if I have over here u is equal to the sine of x, you could say, well, what's du dx? Du dx, the derivative of sine, would just be cosine of x, wouldn't it? Now, you might not have done the chain rule last year like this, but I just want to show you that this is in fact true. Dy dx, and I'm just referring to this right here. It's dy du times a du dx. And let's put this all together. Dy du, well, that's right here, isn't it? It's 5u to the 4th. How about du dx? Well, that's your cosine of x. And then you could re-substitute in with your u. You'd say, well, your u was the sine of x. And there you have it. Now, without a doubt, I think when kids come back to this problem, they'll say, oh my goodness, Mr. Dobner, this is so much more complicated with this Leibniz notation. Look, how about we just do what you said up above? How about we just take the derivative of the outside? In other words, bring down that 5 sine of x to the 4th. Multiply by the derivative of the inside. Well, the derivative of sine is cosine. There you have it. You're done. So it begs the question, why in the world would we ever even write out Leibniz notation? And you might say we're planting some seeds to help you find success down the road in multivariable. In multivariable, you need to set up a Leibniz form, and it's not all that difficult. It's hopefully you can follow through on a test, quiz, whenever, even on the AP exam. You can always do the shortcut, quick way that we've been talking about. With that in mind, let's take a look at example 2. So very often kids will say, oh my gosh, I need to do the quotient rule. Here's the wonderful news. No, you don't. Look, this is 1 minus 2x to the negative 3rd power. And can we take this derivative? Answer, you bet. Derivative of the outside, negative 3 times 1 minus 2x. Subtract a 1. Oh, be careful here. Negative 3 minus 1 is negative 4. And then we're going to multiply in by the derivative of the inside. The derivative of the inside, the derivative of 1 minus 2x is negative 2. So let's just work this out. Negative 2 times negative 3 is a positive 6. Guys, you could leave your answer like this. This would be fine. Of course, we could also write that as just bringing that 1 minus 2x to the bottom. And there you have it. Okay, so that's the derivative of the outside multiplied by the derivative of the inside. Let's take a look right here at number 3. Now, number 3, kids will probably look at that and say, wow, what a shock this is. How come we've got such a ridiculously easy problem? We all know the derivative of cosine is going to be negative sine, so we're done. Negative sine of x degrees. But remember, we need to be in radians. We must be in radians. How do we fix that? Here's how. We've got x degrees, but we know that the link is whenever we have 180 degrees, we've got pi radians. By the way, that little r up here is just a shorthand form to show radians, right? Hope you've heard that before. Hope you've seen that before. Look, the thetas are going to cancel out, and you'd say, well, this would become pi x over 180. Wow. You know what we're really asked to do then? We're really asked to take the derivative of this thing. That's an altogether different problem that will require the chain rule. Derivative of the outside. Well, what's the derivative of the outside function cosine? It's negative sine. There you go. That's the derivative of the outside, keeping the same inner composition. But then we need the derivative of the inside. What's the derivative of pi x all over 180? Well, pi over 180, I hope you could see. Final answer, let's pull that negative pi over 180 out in front. Then we'll have the sine of pi x all over 180. All right. Let's take a look at example 4. Example 4, I guess I really just want to tell you, you might think, holy cow, this looks like a nightmarish problem. A problem where, holy cow, you know, you've got the quotient rule and some ugly derivatives. I would like to invite you guys to take a look at this problem a little bit differently. And here's how. Cosecant is really 1 over sine. Cotangent is cosine all over sine. Now, at first glance, let's be brutally honest, it looks like we've gone from bad to worse. It sure does. However, I'm going to look and I'm going to say, do you know what? Really, what made this problem look so unbelievably tough right now is that we've got the sine of 2x in that denominator. So I'm going to multiply by the sine of 2x on the top, the sine of 2x on the bottom, and of course when I say that I mean distribute everywhere. So what do we have? We've got a 1 up on top because these are going to cancel. We'll have the sine of 2x right here plus, well, oh my goodness, this becomes the cosine of 2x. Wow. I don't know about you, I think this does look a lot nicer. We still have 2 trig functions, but they're nicer, easier, more fundamental trig functions. Also, more to the point, I'm going to rewrite this as the sine of 2x plus the cosine of 2x raised to the negative 1 power. You could think, why in the world would that be helpful? Now I don't need the quotient rule. Wow. So let's work this out. Y prime, I'm going to bring negative 1 down, the derivative of the outside. And I'm going to subtract a 1. That's going to go to negative 2. Then I'm going to multiply by the derivative of the inside. What's the derivative of the sine of 2x? The derivative of sine is cosine of 2x. But chain rule within a chain rule here, you got to take the derivative of 2x, you're going to get a 2. I could put the 2 after the cosine of 2x, I could put the 2 out in front of it. What's the derivative of the cosine function? Well, it's going to be negative sine. But once again, we need to do the chain rule. The derivative of 2x is going to be a 2. Well, guys, right now you're practically done, aren't you? Tell you what, I'm just going to rewrite this, realizing that down below we'd have the sine of 2x plus the cosine of 2x, and that whole thing's going to be squared. That got a little ugly right there. Maybe I can fix that up a little. There we go. And as you distribute -1 up here in these brackets, both of those signs are going to switch. In other words, I won't have a -2 sine of 2x, I'll have a positive. How about we write that out in front? And then the -2 cosine of 2x is going to come after it. And of course, you could factor out a 2 if you'd prefer. You don't have to. Okay, hopefully that worked out rather well. Last one, guys. Example 5. Y equals sine radical 5x. Find y prime. First of all, I want to state the obvious that really inside here is 5x to the 1/2 power. A square root is going to be a 1/2 power. So let's go ahead and take our derivative. The derivative of the outside function, the derivative of sine, is cosine. But here is where I want you to see that this inner composition actually isn't just one function. It's a function inside of another. So I'm going to write that. I'm going to say, look, I need to take the derivative of that inside part. You don't have to write it this way, but as you are reinforcing the chain rule, and especially when kids see it for the first time, I always want to really stress that this is like a chain rule within a chain rule. Inside of the sine function, it's not just the square root of x, it's the square root, but inside of the square root is the 5x. It's kind of like those little Russian teapots where you see a person inside of a person in those little porcelain jars. I think you know what I'm talking about, I hope. And you can say, oh my gosh, inside a sine, it's not just the square root function, but inside the square root, there's a 5x. Well, look, if you're getting intimidated, just break it down step by step. Say, look, how would I take the derivative of that 5x to the 1/2? We're going to do that nice and slowly right now. Here's what you do. You'll say, hey, I'm going to bring down the outside, derivative of the outside, 1/2 5x, this is going to go to the negative 1/2 power. Derivative of the inside, that's just a 5. So now we just clean this up. We could say, well, look, I've got a 5 over 1, I got a 2, so I know I'm going to have a 5 and a 2. I've got a negative power right here, so that's going to come down. And it's a 1/2 power, so if you want, you could keep it as a radical. And then what about up on top? Well, you've got your cosine, and of course inside of cosine you could say, well, I've got my square root of 5x, or 5x to the 1/2 power. That is really all you got to do. So the chain rule is something that the College Board brings up repeatedly. They are obsessed with it. They bring it up time and time and time again. So a problem like this is perfect to get you some extra practice. It's really not like an f of g. It's like an f of g of h of x. And you see the way to do it is just like what we did right here. Just take the derivative of that inside problem, inside composition, treat it like it was a nice simple chain rule, and then you're good to go. Hope this is helping. Best of luck to you.